and after that, there's going to be the lunch break. So the lunch break is slightly delayed, but on the bright side, it's going to last until 2 p.m. So you have the same amount of lunch, just later. All right. So thanks a lot for bearing with all the technical difficulties. I guess it's really on par with a theoretical computer science area. But yeah, thank you. And we're delighted to have the next two speakers, Oded Goldreich and Michal Parnas. So we're going to start with Oded, who really doesn't need any introduction, and I'm not going to even try because that would take the next 30 minutes. But yeah, we have Oded telling us about recent developments in testing bounded degree graphs. Thank you. So I think you're muted, but you can start whenever you're ready. That should be
okay. So I'll start now. Should I start now?
Yes, perfect.
Okay, sorry. Okay, so it's not unprecedented that Dana didn't make it to an event which is having her at the center. Actually, she also didn't make it to her wedding, so I think that's a good start. Okay, so let me start with a quiz. Actually, I didn't mean to say anything personal, but I couldn't avoid this one. So here is a quiz. The question is, but I cannot hear answers from the crowd. The question is whether these two people are the same person. Whether this photo shows the same person.
Okay, so just a quick show of hand. Who says yes? Okay, roughly half, a bit more than half of the people say same person.
Okay, so it's not the same person. One is Dana and one is Camela. The question is who is whom? Camela. Okay.
I think people don't dare taking a guess.
Not there. So on the left is Dana. Okay, so let me start with the talk. So the talk will be about recent developments in testing bounded degree graphs. And I have to apologize that Dana's recent focus was not on this model, but I think since much of her pioneering work was done in this, much of the pioneering work on this model was done by her, this justifies giving this talk here. So let me start with an overview or outline of what I'm going to talk about. First, I will briefly recall the bounded degree graph model for testing. So one thing to bear in mind that all the time I will be talking about bounded degrees. There will be nothing except for bounded degree graphs. The first topic will be studies of graph isomorphism in this model. The second topic will be transporting hardness results about functions to hardness results about this model. In particular, we'll see, I'll claim a separation between tolerant and standard testing in this model. And lastly, I would want to tell you about a very interesting work that I find by Adler, Kohler, and Peng, who is really pivoted at something that I will call constructing a locally characterized expander graph. And this expander graph will be, the fact that it is locally characterized will be used in order to show that that there are graph properties which are locally characterized, but they are not robust in the sense that you cannot test them with a number of queries that doesn't depend on the size of the graph. So that's the general outline in case I don't make it, and I assume I will not make it, but let's start. Okay, so the bounded degree graph model, as I said, all the time I talk about bounded degree. And there is a degree bound D, which is constant, and you can think of 3 or of 13. That's good enough. Graphs will be represented by the incident function. So GVI will be the ith neighbor of V if V has at least I neighbors. Otherwise, there will be a special indication that it has no such thing. We, as a tester, will have access to such an incident function which represents a graph. So we'll get as parameters, explicit parameters, the input size, the number of vertices in the graph n, and we'll get epsilon, which will be the usual proximity parameter. And our task will be to test for graph property capital pi. So we will be given access, Oracle access to the graph by the corresponding incident function, and we'll have to satisfy the following two conditions. The first is that if the graph has a property, then we have to accept either with probability 2/3 or with probability 1, depending on whether we are in the one-sided error regime or in the two-sided error regime. And if the graph will be is epsilon far from the property, then we should reject with high probability, where epsilon far means that one has to modify epsilon d and entries of the incident function in order to make the corresponding graph be in the property. Or in other words, every graph G prime which has a property, the symmetric difference between it and the original graph that is given as input is greater than epsilon d n over 2. The normalization is a normal one. Okay, so that's basically the model, and the focus will be on the query complexity as a function of n and epsilon. I will not mention the dependence on d because I think of d as 3 or 13 and I don't care. So the first thing that I want to review quickly is the problem of testing graph isomorphism. There are two versions of this problem. One has 2 input graphs. So this means that the model has to be modified such that you now have 2 oracles, or if you want, you can pack these 2 oracles in a single oracle in a straightforward way. And the question is, what is the complexity of testing whether these 2 graphs are isomorphic? And the answer is that I don't know, but I know a lower bound, which is tilde of n to the 2/3. So basically, you cannot do it in complexity which is independent of n, which is not very surprising, but you cannot even do it anywhere better than n to the 2/3. It may be that the right result is basically tilde omega tilde of n. I don't know, and I think it's an open, interesting open question of what is the query complexity of this problem. The theorem is proved by an idiotic technique, which is basically reducing it to the problem of testing equality between. So basically, I'm going in the proof where we are going to use 2 families of graphs, but the graphs are all graphs with very small connected components. So basically, there will be connected components of polylogarithmic size, and it will be hard to distinguish whether they are the same connected components or there are different connected components in the 2 graphs. So basically, so it really reduces to testing equality between 2 distributions on n elements. Basically, it's not exactly so, but almost so. And we just apply the lower bound, which from that distribution testing contents. Okay, so that's first result about testing graph isomorphism. The second one, I think I find more interesting. It's about the fixed graph model. So here it's what Ilan Neumann called a massively parameterized property. So the property is specified by a huge object, which is a graph of the same size as the input graph. So this is a fixed n-vertex graph specifies the problem. And the question is whether the input graph is isomorphic to this fixed graph, which is called H. And the theorem which I find interesting is that basically we know the answer for this problem for almost all deregular and vertex graphs. So the answer is n square root of n, basically both a lower bound and upper bound. And it is an open problem whether there are, of course, there are graphs, fixed graphs for which the complexity is much smaller, but the question is whether there are graphs which will not be random graphs. Random graphs will not do the job because of the second theorem, but are there graphs for which the complexity of testing isomorphism to them has a higher complexity than what is stated above. So this finishes the first topic. The second topic starts with a notion. So it's a notion, I'm just rushing ahead and saying that this notion will be applied for property testing in a moment. But right now it is a notion, it's a notion of robustly self-ordered graphs. So what do I mean? The reason for the name will become clear maybe in a few minutes or in a few seconds. But self-ordered graphs are really the same as asymmetric graphs. So it's a different name for the same thing. So asymmetric graph means a graph that you cannot permute its labels and get the same graph. So, or in other words, the automorphism group is trivial. So a graph will be called robustly self-ordered if for any way that you permute the graph, there will be the following thing will happen. If there are k points which were moved by the permutation, then the symmetric difference between the graph and the permuted graph will be omega of the number of non-fixed points. So that's basically the definition. So it's not only that it is asymmetric, it is in a way robustly asymmetric. If you move a lot of vertices from their current location, then there will be a lot of mismatches among the edges. Of course, if you move only one vertex, you cannot move one, you have to switch at least two. If you switch two, then there would be few. Of course, you don't expect that there will be more than 2D, D being the maximal degree. You don't expect that there will be more than 2D mismatches if you move, if you flip, if you switch a pair of vertices. But basically, I'm saying is that you will see as many mismatches as you, in proportion to how many points you move. So that's the basic definition. And so that's the definition of being robustly self-ordered. Now I want to give a definition of what does it mean to be locally self-ordered, and this will really explain why I call the whole thing self-ordered. So I'm talking about a graph, and it's a fixed graph, so everybody knows it. And what I'm giving you as an oracle, you are given as an oracle access to a graph, to a different graph, which is isomorphic to the graph G. And your task is to find the location of this vertex, not the location of this vertex. This vertex is not in the graph, but the vertex which is analogous to it or is mapped to it by the unique isomorphism. It is a unique isomorphism because the graph is asymmetric. So your task is to find the location of the copy of the graph G in the copy of the particular vertex V prime, its copy in the original graph G. And I want to do it using very low query complexity, so polylog in V. So that's the definition. So I threw at you two definitions. I find so of course the locally self-ordered is a stronger condition than just saying self-ordered. Self-ordered will say the following: if I give you a copy of the original graph, then you can really find the unique isomorphism which maps it to the original graph. So this will be self-ordered. locally self-ordered makes this in a local sense. So for every vertex, you have to locate it, making few queries to the copy. Of course, to the original graph, it is in your head. You have the direct access to it. You know it completely. The point is that I'm giving you access to an isomorphic copy, which can be a random isomorphic copy or an arbitrary isomorphic copy, and I'm asking you to identify vertices of it with respect to vertices in the original graph. And the two theorems which I'm going to give without proof are that there exist robustly and locally self-ordered graphs, and furthermore, they are strongly constructible. So it's not only that they exist, they are constructible, and not only that they are constructible, they are strongly constructible in the sense that given a vertex, you can compute its neighborhood in fast time. So basically, that's a normal notion that you use about strong constructibility in expanders, for example. The second theorem is that if the graph is locally self-ordered and it has a small diameter, so you have in a way a reverse local self-ordering. So local self-ordering said that if you are given a graph in the copy, you can find the original version in the original graph. And the reverse says that if you are given a vertex in the graph itself, or if you select the vertex in the graph itself, you're not given, because remember, you have the graph G in your hands. So for every vertex in the graph G, you can fairly quickly locate it in the graph G prime, meaning fairly quickly means by making not too many queries. So these are the two theorems. And now finally we get to property testing. So, and of course the theorem doesn't say it, but I'm going to say it, that the proof of the theorem will use the previous two theorems in a way. So basically the theorem says that there exists a graph property that it is easily testable, but tolerantly testing it requires almost linear query complexity. So here is a typo. This is for the bounded degree graph model. So everything is for the bounded degree graph model. So I already hinted this theorem will be proved by a transformation from an analogous result that refers to functions or to strings. So the proof idea is the following. You start from an analogous result for property of strings, which was obtained by using PCPs by Fortner and Fisher, and you now transport it. How do you transport it? You do the following. You encode so you want to do a transformation from strings to graphs, to bounded degree graphs. And the point is that that we are talking about graph properties. So in string, the string has an order, but a graph doesn't have an order. Point is, of course, that I said that I'm using a self-ordered graph. So this is why everything makes sense. So you are taking this string and you are encoding it in graph. How do you encode it in the graph? You do it by attaching tiny gadgets to a graph which is robustly self-ordered and locally self-ordered. So we know the existence of such a graph from theorem 1. The fact that it is efficiently constructible is less important for the theorem as stated, unless you want to say that this property is even easy to recognize. So what is going on here? So again, I don't see your faces, so I don't. So that's really annoying. So basically, I'm taking a string and I'm encoding it in a graph, which sounds, unless if I didn't have these properties I'm talking about, it would be insane, because you can say the order of the string is not preserved by the graph. But the fact that the graph is robustly self-ordered says that it is preserved. And this is what we are doing. So we want to prove hardness of tolerant testing. we do it by reducing, the reduction also works for non-tolerant, for general, but here I want to do it for tolerant because I want to show a lower bound on the graph property. And I'm going to use a lower bound that I know on tolerant testing of the string property. So basically I'm reducing tolerantly testing the string to tolerantly testing the graph. And here I'm using, I'm not using the local self ordering, but I'm using the robust self ordering feature. So I'm using the fact that you cannot change move around the string. If you move around the string, you move around the graph, and if you move around the graph, the basic graph, then there are many mismatches by the robust properties that I discussed before. So that's the hardness of tolerant testing. Now I have to talk about the easiness of standard testing. And the easiness of standard testing, in order to show it, I reduce testing the graph to testing the corresponding string. But the point is that I don't know the names of vertices in the graph, or I don't know the location of bits of the string. And for this, what I have to do, I have really to do I have to use the local self-ordering feature and the theorem 2, which I discussed before. So that's a very high level. I don't expect anybody to follow it, but just have a feel of what is going on here. Okay, so I'm moving to, unless there are any questions, I'll move to the next result, which is the last result.
There is a question by Sohail.
Is there any hope of proving the same for a natural graph problem? Or is there any candidate graph problem for which you think this separation exists?
I don't know, but you have to refer the question already to the string world. I don't think that there is a good, as far as I don't remember, Dana may know better tomorrow, but I don't remember on top of my head a very natural property of strings or of functions which shows a gap between standard testing and tolerant testing. So as I said, the only proof that I know goes by PCPs. So of course it creates an unnatural property.
Any other question? Also, you should be able to see the audience maybe now. I move my laptop. So
I see the audience, but it's very small. So if anybody has a question, you can transmit it, or we can continue. I think the last part will be more interesting to most people.
So yeah, I'll be monitoring if there are questions.
Come again?
I'll be monitoring in case there is any question.
Okay. Okay. So the last topic, which I find amazing, is the notion of local characterized graphs. So there will be a notion, and there was a notion, and we'll talk about it in the next slide, of locally characterized graph properties. So this is a collection of many possible graphs which is characterized locally. But I'm talking about characterizing a single graph locally. So what do I mean by local characterization? The local characterization there are several ways of defining them, and they are not equivalent, but the result holds for all of them. The one I prefer is that the local characterization is given by a set of tuples of local views in the graph. So basically, you are given a set of many tuples. The size of the tuple will be also a constant, and each of the things is really showing you a neighborhood of a constant diameter from a vertex. So you have all say that you have three possible tuples like this, and so the three things show three possible neighborhoods that vertices can have. And the condition says that this is only the graph must satisfy this. So for every selection of 3 vertices, if you go to distance 5, what you see is these 5 subgraphs. And that's basically the definition. In a way, okay, so that's basically, I'll give you an example because maybe it will clarify the notion. Suppose that we are talking about a graph which consists of isolated triangles. So I claim that this graph is locally characterized by a single tuple, which says that if you select any vertex and go to distance 2, you will see a triangle. But that's a very superficial example, and I would challenge you to find more interesting examples. But I want to say that in contrast, typical expanders are not locally characterized, because typical expanders, if you look at the neighborhood of a graph, what you see is a tree. So this doesn't specify a unique graph, because all constructions of expanders and also many other graphs, if you go to a constant depth neighborhood, you will see a tree. So that's basically, it characterizes maybe the property of having a large enough gears, which is greater than the constant that I take. But this is not a unique graph. So the theorem says the following, it says what is in the title, that there exists and actually can be easily constructed, relatively speaking, an expander graph which is locally characterized. So I find this quite amazing. And the proof idea is really to superimpose a full DRE, D will be a large constant, with a specific construction of an expander graph, which is a zigzag construction. It will not take the zigzag construction itself, but it will take all the copies of the zigzag construction up to the size that you are interested in. We'll see it in a moment. And this D of the DRE tree is the cloud size in the zigzag construction, and we'll see it in a moment. So basically, I'll show now the construction. So I'm saying the same thing. So I just want to remind you, so actually I will be talking about the replacement product instead of the zigzag product. It really doesn't matter. So basically what it does is the following. If in the original graph, there was a vertex between, there was an edge between vertex U and vertex V, and remember each of these, and assume that the degree in the original graph was capital D. So if there was such an edge, then you will see 2 clouds in the new graph, and the clouds will be expanders with it makes no sense because D is a constant, but the degree will be a smaller constant, and there will be a sufficiently good eigenvalue gap in there. But forget this detail. So basically, there will be a cloud of size D. D is the same as the degree in the original graph. And these 2 clouds will be connected by a single edge. And the single edge will go from the ice vertex of one cloud to the jth vertex of the other cloud if there was a corresponding. So if the edge going from U to V was using the ice port in U and the jth port in V. So basically, that's a natural construction. And what, so this is, for cheating, this is a zigzag product. So the original graph is on top, and the resulting graph, which is D times bigger, is on the bottom. And the zigzag construction actually is an iterative construction, which takes the case graph in the construction and does the obscene thing with it, like raising it to the power 10, just to be on the safe side, and doing a zigzag product with a fixed graph H. And the fixed graph H is the one I was talking about here. So in such a way, you get the K+1 graph. So that's the iterative. This is the result of Reingold, Vadhan, and Wigderson. So, but I'm I'm taking it as something and doing something with it, and not me, Adler et al. Did it. So basically, what they are doing is the following. As I told you, the graph, if you want to ask how will the graph look like, the graph will have many layers. So you have to tell me what size of a graph you want. By the size of the graph you want, I will determine how many layers to use. And what I will put in each layer is a different graph of the zigzag construction. So basically, in the case layer, I will put the case graph of the zigzag construction. So the graph that you get after doing k iteration. And now I will superimpose these graphs, these layers with a DRE3 in the natural way. So the natural way will be the following. Each vertex in layer K is connected to all vertices in its cloud in layer K plus 1, and etc. Same for every vertex. And furthermore, the edges which are going from this vertex to the next vertex, and now I'm cheating a bit, but you can easily replace it by gadgets. They are directed edges, and not only that they are directed edges, I'm using D colors, so they are colored edges. So basically, the edges which are going from layer K to layer K plus 1, from each vertex you will have D different edges, and these D different edges will be colored with D different colors. And these colors will really tell the vertex in the cloud what is its identity, which will be crucial to make the local conditions. So basically, the local conditions will now say that if in some layer, and I'm not telling you in which layer, because this will not be a local condition. I'm saying if in some layer, vertex U is connected to vertex V by an edge which is colored IJ, so these are also different colors than the ones I used before, but there are only a constant number of colors. Maybe D squared colors or whatever, I don't care. So if you have such an edge, then you will be connected by an edge colored I, directly connected to the next layer. So it's not said that it is the next layer, but there is a direct edge colored I going from you, and a direct edge colored J going from V, and these two will be connected by these two endpoints of these two things will be connected by an edge. So basically, all that I want you to feel is that these are local conditions. All these things that I'm saying are local conditions, and the expander, the way it will look, it will just, as we said, it will be a DRE tree of a particular depth. So the graph is not unique up to its size. It is it's unique only within its size. So the graph will have this number of layers, and in each layer you will see the corresponding zigzag iterated graph, and the directed edges will be as a tree, as I was saying. So basically, the structure of the graph, if you look at it, it's a very weird graph. But the point of this weirdness is to allow me to characterize it in a local manner. So this is what I was doing, or they were doing. So if there are any high-level question about this, so basically, it's a very unnatural expander graph. I'm not claiming it is a natural expander graph. It's a very unnatural one, but it is an expander graph, and it is locally characterized.
Was there a question there?
I just wanted to know how do you
set up the local properties so that it's possible for the construction to stop at some layer.
Yeah, okay, so there will be also, I didn't specify all the conditions, but there will be also a condition saying that if so the interlayer colors are different than the edge colors. So basically we'll say that if you have no vertex, no edge going out of you, then also your neighbors with the colors which are interlayer will also have no neighbors. So basically it will say that everything stops in one layer. And I forgot to say there is also a root to this tree, and you have to initialize it. So I also have to argue that there is only one vertex which is has no incoming edge and has the outgoing edges. So there are details here. I'm not claiming that it is obvious that what I said works, but I think that this is basically the idea.
And just to confirm,
I'm arguing that it works, but I'm not arguing that you are supposed to see that it works.
And just to confirm, for a given little d and n, there is only one such graph. This is
yes.
Okay.
For every so basically, note that not all graph sizes are possible. Some graph sizes cannot satisfy this. So for every size which is adequate, which you can see what it is, it's basically the sum of powers of d. So for every such thing, there is a unique graph up to isomorphism. So if you talk about unlabeled graphs, then there is a unique graph of this type. Okay, so I think this is believable. I don't claim more than that at this point, but can see where it is going. And of course, this construction is not, you can do variation of it. It really doesn't matter if it is zigzag or replacement, and it doesn't need to be an expander. I want it to be an expander for the next slide, but it could work also for graphs which are not expanders. But basically, they will uniquely characterize a graph, given the number of vertices in it.
Hi.
Okay, so this.
Oded, actually, I think we're a bit over time, if I'm not mistaken. Yeah. So, yeah, just I don't know how much more do you have left.
It's just one slide, so
Okay,
we're
great.
fine. Okay, so just let me just make the connection. Basically, the reason that they constructed this graph is in order to show the following theorem, that there exists a locally characterized graph property. So now we are talking about graph properties, and that's a well-known object. There are examples of it, like, for example, a subgraph freeness or induced subgraph freeness are locally characterized, of course, but there are more than that. So there are graph properties that are locally characterized, but not robustly locally characterized. The robustness is a notion that Madhu and Ronit were using, Rubenfeld Sudan. Not only that they are not robust, they are even not testable within size oblivious. So not being robust can mean also that there is no proximity oblivious tester, but I want to claim even more that there is no tester at all which has size oblivious query complexity. And what I want to claim even more is that I even know a lower bound, an explicit lower bound, which is pitiful, but it's better than nothing, which is 4 times log the size of the graph. So basically, how does it come about? The first part, the existence of the non-existence of size oblivious query complexity follows from the fact that there is a paper, I forgot the name now, when I will not look it up, but you see it in the next slide, that is showing that if there is an infinite property of graphs that is testable in size oblivious query complexity, then it contains an hyper-finite subproperty. So subproperty is a subset of the property. So basically, it's totally non-explicit, this theorem, but it's a nice theorem. And basically, it says the following. No, look, we constructed the property. The property has a unique graph in every size. And this graph is an expander. So there is no subproperty which contains hyperfinite subproperties, because I didn't say what hyperfinite is, but hyperfinite is strongly non-expanding. So you cannot have such a thing. So immediately you get a non-explicit statement that there cannot be a size oblivious query complexity, and a direct analysis of the specific graph gives you a log bound. So, and you can get a better bound if you slightly, which is optimal for this construction, if you slightly relax the model. So if there is no question, I'll get to the last slide, which is just the references, which I forgot.
Oh, actually, there are two questions.
Okay. Yes.
What is log of the number of quarks in the universe?
This I don't know. I'm not a physicist.
Probably smaller than 10.
Okay.
So have you considered GI testing in general query model?
I didn't hear, sorry.
So have you considered graph isomorphism testing in general query model, say for one known, one unknown case?
I'm very sorry, I didn't hear well.
So the question is,
can you repeat?
Yes, I'm just going to repeat it closer to the mic. Have you considered isomorphism testing in a general query model?
Is a general graph model, you mean?
Yeah, in a general graph query model. Yeah.
So firstly, let me say I didn't mention it because so in the dense graph model, graph isomorphism was studied, and there are upper and lower bounds of the type number of vertices up to something. They are not always tight, as far as I remember, but I didn't want to mention it because it's in a totally different model. Is a general graph model I didn't consider. Of course, the lower bounds should hold, I believe, but I don't know what will be the upper bounds. I would assume it is hard. It's even harder, but actually I assume that it is also hard in, well, depends if you are talking about the fixed graph or the unfixed graph model, but basically, yeah, the simple question is that it is out of scope, because I'm giving a talk only about the bounded degree graph model.
I ask a question on that. So you have a lower bound, so there are some properties which require at least log n. Could you come up with an upper bound?
I don't believe it's the right answer. It's
no,
just
I know.
Better than nothing.
I know, but my question is it feasible that, for example, every locally characterized graph property is testable with complexity at most log n?
The point is, until 3 years ago when Adler et al. Came, I was conjecturing that I was leaning to say that it is size oblivious. So I was already proved wrong once, and I don't have a good intuition. So the first thing will be to cut off this log. I think either with this construction or with some other construction, but I don't know.
And I have maybe a small question about, is there any other application of this type of graphs, maybe for like deterministic amplification or things like this?
You mean the locally characterized graph or the robust graphs, which I was talking 2 slides ago?
The one you just gave, that was a combination of the Zig-Zag graph and
this one. I don't know. I find it a very fascinating result per se, counterintuitive in a way. But yeah, there could be. I don't know. I didn't think of it.
Thanks.
Let me just put references. So as I was saying, there is no reference to what I needed, but it doesn't matter. Okay, so let's skip it.
Thank you. So yeah,
So the result I was previously forgetting to mention, I don't find it now. Sorry.
Well, let's thank Oded, and yeah, the slides are